And thanks everyone for attending the webinar this morning. Appreciate your time. Today we're going to talk about replicating human vision in near-to-eye display applications. And just a real brief summary about Radiant. We're experts in measuring light and color, automated visual inspection, and we have global support, a number of offices worldwide, and a team of engineers that travel fairly extensively to support our systems around the world. So let's talk about today's agenda. We are introducing a new device, which is a near-to-eye lens, which is designed for measuring near-to-eye displays. And we are going to discuss the challenges of measurement of near-to-eye displays, what kind of current methods could be used, and what are the challenges of those current methods, and what is important about replicating, what about human vision is important to replicate: high-resolution imaging, aperture size, aperture position, capturing the full field of view of the devices that are available. We'll talk about the solution that Radiant is introducing, and then we'll have some time for some questions and answers from the audience. So let's talk about challenges in measuring near-to-eye display systems. The first thing is kind of, why are we doing this? And Radiant has seen, and the world has seen, a pretty substantial growth in the market for AR/VR devices. And we don't really see very many good solutions available on the market, available to do the measurement of these devices. Radiant sees itself as a leader in display inspection, and as display technology adapts, changes, Radiant needs to be adapting and changing and continuing to offer top-notch solutions for these different applications. These displays are unique in the fact that they will be viewed extremely close up. Radiant supports a number of applications for more standard display technologies like monitors, tablets, mobile devices. Those are all going to be viewed at a distance, whereas a near-to-eye device is probably going to be just a few centimeters from the pupil of the human eye. These devices tend to have an extremely wide field of view to attempt to replicate a scene that would be presented to a human. And they also are viewed within a head-mounted device. And so there may be some mechanical interferences associated with the goggles themselves. So what are common applications for near-to-eye devices? Virtual reality is probably the most understood, the most well done, used, and available on the market today. There are a number of augmented reality and mixed reality solutions as well that are gaining some traction and are very interesting and some really exciting technology. So a near-to-eye display, by definition, is viewed near to the eye. Any projections that are delivered into the eye are going to be magnified with a very wide field of view, and any kind of defects that are apparent on a display for a wide field of view device tend to be quite noticeable. That there can be screen door effect from pixelation of the displays, any kind of dead pixel or non-uniformity of the pixels could be pretty detrimental to a user. These devices are fairly expensive and new, so if somebody received one, there were a bunch of dead pixels, it's likely that would drive a return. So these devices tend to project a very wide field of view into the human eye, and so we need a solution that can simulate the field of view of human vision. And human vision varies from person to person, but 120 degrees is a pretty good equivalent of human binocular field of view, horizontal field of view. Here are some examples of some devices that are commercially available on the market today. You can see that the field of views specified by these manufacturers are all approximately 100 to 110 degrees. In some cases, these are horizontal field of view. In some cases, these are vertical fields of view. And but approximately everything that we've seen so far falls around this type of range. So these devices tend to be in some kind of head-mounted display. A compact optical system is required in order to be able to get the imaging device to the position that they need to be so that they can be imaging the device at the same place that a human eye would be imaging it if they were using this in a standard configuration. What kind of measurement criteria might someone want to analyze with these types of systems? Luminance and color are definitely of interest. Image clarity is kind of a big one. The optics that are being used to render these displays at infinity or some particular working distance tend to be relatively complex, and because of the fact that these need to be mass-produced devices, there are trades that are made on the optics, and so quantifying the effect of those optics or also characterizing devices to see if things are meeting spec is something that could potentially be quite interesting. There tends to be some distortion from these devices, and that's something that we might want to characterize. And also, if you want to qualify the optics or a fully assembled system, confirm that the alignment is done correctly, all this kind of stuff, these are things that you might want to test. And then also focus uniformity. The focus on these devices tends to be relatively ununiform, and so it might be something that would be interesting to characterize. And then also, one of the main specifications that manufacturers are listing for these devices is the field of view. And the field of view can be a little bit of a subjective specification. It can be dependent on the exit pupil of the device, the observer, the pupil, the entrance pupil of the observer. And so the specification may say one thing, but it might be very interesting to actually verify what the true field of view of the device is. So there are some existing methods, and I've seen a number of people try different ways to measure these types of devices. And some solutions are somewhat viable, but there are other solutions that have been really very challenging. And so I just want to touch on a few of these different options that are available and the various challenges associated with utilizing those. So let's go over the options that we have available here. So there's machine vision cameras is one potential option. We'll talk a little bit about the challenges of that. Basically, there's limited resolution on a machine vision camera. Standard optics is something that you would most likely be using with a machine vision or some other kind of camera system. That can be very challenging for these types of devices, and we'll go into the reasons behind that quite extensively in a moment here. Custom optics, always a solution. It's a fun project for your optical engineer, optical designer. It also tends to be very time-consuming, very expensive. Anyone who's been involved in any kind of complex optical design generally knows that the first design is usually maybe not so good, and it's going to require some revisions. And then also things just like tolerancing of the optics and being able to manufacture them repeatably and consistently are all considerations that have to be taken into account if you plan on developing some kind of custom imaging system for this type of analysis. And then test software is required also to perform these types of analyses. If you're going to be developing those for your program, software engineers are clearly relatively expensive, and it may take some time in order to provide those solutions, and they may not be very mature or robust. So machine vision camera is certainly an option. The main issues that we would have here that I think a lot of people who would be interested in doing this would have is that typically a machine vision camera isn't going to give you a calibrated luminance value. So you may get some kind of relative information that could be interesting, but you wouldn't know specifically what's going on, what kind of absolute values you're seeing of the luminance, and in particular color. Most of these devices at best may use a Bayer system for emulating color vision, and it's very unlikely that they would be able to give you very accurate color rendition and report accurate color coordinates. There are other things that would be different about a machine vision system, things like vignetting, distortion. All of these optical effects can be calibrated away to try to make the imaging system appear more like what a human really perceives. And those types of calibrations are generally just not available with a machine vision camera system. And so you would be kind of on your own with something like that. And then also a low signal to noise ratio. This can actually be pretty important for this application. A lot of these displays have extremely high contrast ratios. And in order to accurately measure those contrast ratios, most likely you would need a pretty high signal to noise ratio. And a CMOS camera with an uncooled sensor just is not going to be able to give you the same kind of signal to noise ratio you would see with a scientific grade CCD that's electronically cooled and temperature stabilized. Just to touch on limited resolution a little bit more, most machine vision cameras are not going to have particularly high resolution, and the resolution of these systems that we're inspecting tends to be really quite high. And the goal of a near-to-eye display is generally to try to replicate a field that a human may actually perceive. And to have a more immersive experience requires high resolution so that pixelation effects are just not really apparent to the observer. And with that high resolution, if you want to detect things like non-uniform pixels or pixel defects, a really high resolution sensor is going to be required in order to capture that kind of information, especially if you want to do it in a single shot. Okay, let's talk a little bit about standard optics. So there are obviously many different kinds of lens options available for cameras and photography. Radiant offers a series of lenses for its standard display inspection products, which are valid for regular displays depending on the field of view, the working distance, these types of considerations, the amount of light that's available on the display. These lenses generally are just not adequate for measurement or characterization of a wide field of view near-to-eye system. There are a number of problems. One is just the physical size of the hardware. It would be difficult to get one of these large lenses into the same position as where an eye would be located inside of one of these heads-up display goggles or near-eye goggles. The aperture is probably one of the most critical components of this, and we will extrapolate on this quite a bit more in the next couple slides. But effectively, the entrance pupil of the optical system needs to be as close to the front of the optic as it can possibly be, or even in front of the optic. And the entrance pupil for most standard lenses tends to be where the adjustable aperture is located inside of the lens itself, the lens body, the barrel of the lens. And that tends to be pretty far back from the front of the device. So it's effectively going to be impossible to get most of these devices to have the entrance pupil be located where the human pupil would be located if they were actually using the device in a standard use case. And then field of view is another big issue here. There are certainly standard photography lenses that have very wide field of views, but there's going to be massive distortion associated with those types of lenses, and again, the aperture becomes a real problem. So let's talk about the obstructed field of view from a standard lens. You can see in this diagram here we have the camera aperture, which is effectively buried inside of the lens itself. And then we have the exit pupil of the AR/VR device shown on the left. And you can see that the AR/VR device has a display which should be imaged out to the outside of the dark gray area. But because of the aperture of the lens itself, we're occluding the vision of the display, and so we're only able to see a very small section of it. And again, we'll touch on this a little bit more in some later slides. Custom optics, again, fun project, exciting for your optical engineer. The problem is that any kind of custom optical solution really tends to be very expensive. Just the design itself can take a long time, and then procurement is also going to take a considerable amount of time. Most of these solutions will be developed for one very specific application, and so it may not be possible to redeploy this design for other types of applications. And then, of course, you're really going to be on the hook for supporting it because it's your design. So made in-house software, again, a lot of expense associated with this, a lot of time to develop, and if there's a solution that's available off the shelf that does what you want, 90% of the time it's usually better just to buy it rather than build it. Okay, so let's touch on some technical advantages of Radiant's solution. So this near-to-eye device is designed to measure all of these types of applications. So VR, AR, mixed reality, we've had success with all of these types of systems, and these are the various applications and types of displays that would be used in these devices. Imaging is important for this type of solution. You may be very interested in what's going on in many different areas of the display. You may be looking for some kind of mura, like a blemish on the display. You may be interested in the uniformity of the display. And you're just not going to be able to capture that information effectively with a spot meter. And you could potentially, but then you may be scanning a lot, and the cycle time could be very extensive. And so, Radiant is trying to design a solution that certainly is applicable in the laboratory, but we also really try to support production applications, and we would expect that this could be done as a final assembly test. This is just an example of various types of tests that we have available for the system. We can measure all kinds of different things, analyze different types of phenomena that you would see in these devices. High resolution, obviously you're going to get a lot of detail. If you have multiple CCD pixels per display pixel, then the amount of dynamic range you'd be able to see would be increased. The level of the defects would be, the level of the defect that you could perceive would be greater. You would have more resolution as far as the dynamic range is concerned. This is just a quick example of a test that's designed to find some point defects. So here's an image. We've generated a local contrast, and we found some defects in this image that we're highlighting to the operator that could go into a report. So replicating the human eye, what's required for that? We want to try to simulate the eye pupil size, and we don't want to sacrifice too much in the same process. We also want to try to get the entrance pupil of the optic located at the same place as the entrance pupil of the human eye. And we also want to try to cover the approximate field of view of human binocular vision, which is going to be approximately 120 degrees, and that's what our system is designed to capture. So what's important about designing this to replicate the size of the human pupil? Basically, we want to try to image the device the same way that a human would see it if they were using it. And so we're trying to replicate approximately the pupil size of a human. And if we were to make the pupil really, really small, that might make the lens design easier. But then we would be really limiting the light that could make it to our sensor, and so exposure times would be extra long. Any kind of vibrations would really affect the system. Making the pupil too large would make the optical design exceptionally challenging and much more expensive. So we have compromised on this specification, but we believe that it's a fair compromise. So human perception, we're talking about the aperture position of the optic. This, you can see that if the aperture is internal, we're going to be occluding the display. If the aperture is at the front of the optic, then we can visualize the entire field of view. Again, looking at what a standard lens looks like, aperture is buried inside of the lens. With this lens that's designed for this type of application, it's really important that the entrance pupil of the optic is at the front of the lens. And so now we're able to get the field of view that's desired, and we're not occluded by the exit aperture, the exit pupil of the device that we're looking at. And this is just to try a way to try to visualize what I'm discussing here. So if the entrance pupil is far from the exit pupil of the device, you would see the image on the left. Effectively, the image is occluded, and you still can see some of what you're trying to look for, but a lot of the sensor space is effectively wasted. And then if you can put the entrance pupil at the front of the lens, then the field of view is well utilized, and we're able to get around the occlusion of the exit pupil of the device. And then human vision, about 120 degrees. That's what these devices are being designed to try to meet. And that's what humans perceive. Okay, so we have Radiant's solution. So this is a Radiant eye camera with the near-to-eye lens, the AR/VR lens attached. So the lens works with either the I16 or Y16 or I29 or Y29. For the full resolution, the 29 megapixel sensor is required because it's just simply a larger sensor. For color applications, the I camera is needed. If color is not important, then the Y camera is luminance or radiometric. So to review, the aperture is located at the front of the lens, and that's how we're able to image these devices effectively. We've chosen to use a 3.6 millimeter aperture, which is a good compromise between a constricted pupil, a fully dilated pupil. The field of view does hit the 120 degree requirement. That's a horizontal field of view. And then we also are able to do a distortion calibration, because this really is like a fisheye lens. And you would normally see an image that looks like the one on the left with a lot of barrel distortion. After you apply Radiant's distortion calibration, you would see a normal appearing image. What we're viewing here is just a standard rectilinear grid pattern. TrueTest software is something that would probably be important to come along with this device. TrueTest is a testing sequencer software that can control a testing suite. We have a number of tests that are available that are good for standard displays. We've also developed a number of tests that are pretty good for this specific application. So things like slant edge MTF, image distortion, measuring the device's field of view, and then also having the device or the system read out in degrees. So when you're looking at a virtual image that's focused at infinity, we can't really indicate where a pixel is in meters or centimeters. We really need to report that in degrees. These are just examples of some of the standard display tests available in TrueTest. ANSI brightness, point-based uniformity. We can look for pixel line defects, mirror defects, J&D. Image clarity, really important for these types of applications because of the optics that are used to relay the image from the display to the human eye. And often this really needs to be characterized. So there's a number of ways to do this. Primarily, this is going to be done with some kind of MTF test. So there's an ISO standard that's written which describes how to do a slant edge test. We have a test based on that. And then there's also a line pairs test, which we also have a test to handle. So slant edge contrast, this is just an example of what comes out of this. You present a slanted edge to the system so that pixelation doesn't cause a major problem. And we sum up many different cross sections of this, which is the chart you see at the top. We take the derivative of that cross section average, and then the FFT of that becomes the MTF curve. And this report is available with the test. Line pair, another way to assess image clarity. We're presenting horizontal lines on the device, and then we're looking at the contrast in these regions. Okay, various headset effects that can occur. Distortion certainly is interesting to understand and characterize. That could potentially help you understand the alignment of the system. And it also might be interesting to characterize the distortion of different colors to see if there's any kind of chromatic aberration associated with the system. So the field view test is something that we've developed specifically for this, effectively as a way to verify specification, that what is the real field of view of the device when it's imaged in this way, and that can be reported out to the user, to the engineer. Spatial positions given in degrees, pretty important. Software testing in a sequence. TrueTest is a highly optimized testing sequencer. It can run fully asynchronously. It's really well pipelined. I'm under pressure constantly to try to improve the speed of our systems, improve the speed of our deployed systems, and being able to take advantage of multi-threading, CPUs that have many, many cores. All modern computing is all taken advantage of with the software solution. And then the API device interface, this really shouldn't be discounted either. TrueTest is very modular. If you have developers available, then they can actually help to construct interfaces between the testing sequencer and the device under test. And just to touch on that, we wrote a new device interface, which we call the I think AR/VR video pattern generator, which a lot of these displays, the way that you drive a signal to them is you give it basically a duplicated signal, a left and right image that are identical. And so we have a device or interface that is a video pattern generator, which will output those patterns on a HDMI or DVI or whatever kind of video output you have on your PC. Just an example of what a test sequence might look like. Many different patterns. Each pattern can be analyzed for as many different types of analysis as is required. The sequencer takes care of understanding what measurements are needed, what measurements are not needed. It just takes the minimum number of measurements required to be able to perform all of the analysis that has been asked for. And all of this can, again, happen asynchronously. So analysis is happening while the camera is measuring. So the solution that we're proposing is this AR/VR lens, which we've developed. This has taken us quite a bit of time. This is a further revision, and it's working quite well. We're really happy with the results that we've seen so far. Our prometric imaging colorimeter, and then TrueTest software, and specifically our TrueTest AR/VR module is going to be very appropriate for this application. So in summary, growth of embedded and AR/VR markets really requires Radiant to step up and come up with a better solution for imaging these types of devices. We've had some success with this in the past, but I've really pushed the company to have something available that can really work for many different types of customers and many different applications, and this is the fruit of that. Standard display measurement systems really are not appropriate for this application, and you're going to run into a lot of trouble with trying to use them. And our solution is the only one that we're really aware of right now that can replicate the human pupil size, position it within goggles, and capture the full field of view. I mean, we're well aware that there are many features that might be wanted to be added to this, but we really wanted to bring something to market that could be available right away so that we could start to get some kind of feedback from our customers and also get things into people's hands that they can start to use for these types of tests. That's what I've got. So
okay, thanks, Eric.
Thank you.
Thanks for that great presentation. We appreciate you guys sticking through here to the end, and we are coming up on our Q&A portion of the presentation. For those of you that have to take off, you have other obligations, we appreciate you joining us, and feel free to reach out to us at info@radiantvs.com if you have any additional questions that didn't get answered. And then right now I'm going to look at our questions window here in the GoToWebinar interface. If you have any questions for Eric, please go to that window in your GoToWebinar interface and enter a question there. We'll be queuing those up here just a second and reading those out for you. So I'll be showing Eric these questions here.
Okay, so I see one which is what is the vertical and diagonal field of view of the lens? For the 29 megapixel system, we spec the full horizontal field of view as being 120 degrees. It's going to be 80 degrees vertical and then 144 degrees diagonal. And the I-16 is another option. The field of view is going to be a little bit lower on that one, just because the sensor is slightly smaller. I see there's a question about the price of the system. We certainly will have someone contact you to follow up on that information for you right away. Full spec sheet of the system. Shayna, I think you can probably take that one.
Yeah, sure. Actually, we have a spec sheet for our lens currently. We're developing one for our software module. It's a modular system in a way, so we do have a spec sheet for the lens, the camera, and the software. But if we needed additional specs for the combined solution, we would have one of our sales or engineering staff reach out to you and answer those questions for you.
Okay, I see one here that can the lens be exchanged with standard optics? Certainly. So the lens is just basically, it screws onto the front of the camera, it has a focus capability, and it can be replaced with a standard lens as well. So the camera itself can be used for multiple applications. Is there an ability to change the aperture size? That's a great question. We've chose the 3.6 millimeters as a compromise to try to get a good MTF of the lens itself, but also be able to get enough light to the sensor. We can adjust the aperture. So that's something that we could take under consideration for a specific application. We've had some customers that we've needed to adjust it a little bit. Minimum spec for the PC required. I think that we would have that listed more in detail on the spec sheet itself. I would really recommend a 64-bit system at the very least, just because the 29 megapixel sensor generates a lot of information, and it really bogs down on a 32-bit system. So RAM is pretty important for this application. If you're doing any kind of like automated testing or the takt time of the system is really critical for you, then basically the faster PC, the faster the whole system is going to run. We've done a pretty good job lately of being able to get the critical path of the system down to the camera acquisition time itself. So as long as your PC is very fast, then we're only going to be limited by the speed of the camera. Position of the entrance pupil of the lens, it's right at the very front of the lens itself. Minimum eye relief the system can be set in front of the headset of the lens. I think that's really kind of a physical constraint. Basically, as close as you can bring the optic to the lens is the closest you can bring it. It's designed to try to taper down a little bit at the very front. So if there's any kind of interference, or if you wanted to do some kind of scanning or something like that, that would be a possibility. Let's see. Are measurements correlated from one eye to the next? That's an interesting one. One application that we've seen is trying to balance displays. That a lot of these devices have one display for the left eye, another display for the right eye, and the manufacturers want the device to look uniform and not have one display have too much red and the other display have too much blue. So color balance, gamma correction, these are things that can be accomplished with the system. How does the system cope with temporal aliasing caused by time sequential color displays? Great question. The simplest way is to choose an exposure time that's long enough that it will just capture many cycles of the system itself and integrate those. That tends to work relatively well. But it could be that the device that we're looking at is exceptionally bright, and we may not have that convenience because we're already saturating the sensor. in that situation, an ND filter or something like that might be a possibility, but it's probably not desirable. What we've typically been able to do is recommend that we set the exposure time as even multiple of the cycle time of the device itself. So say it's refreshing at 60 hertz, that might be like a 16 millisecond cycle time period. So you would want to choose 16, 32, something like this. And we've written some device interfaces where our customers wanted to auto-adjust exposure, and we had auto-adjust exposure effectively snap the exposure time to an even multiple of this periodicity of the system itself. Let's see. So which MTF test is more effective, slant edge or line pair? It depends on the application. The slant edge test, we wrote it to try to meet the ISO standard. We've had trouble with the slant edge test in some situations when the pixelation of the device is very high. We'll actually pick up the frequency of the screen door of the system, and that can interfere with the MTF report. I see there are some questions about the MTF and the capabilities of the lens itself. We do have that information, and we can provide that on a case-by-case basis. So certainly reach out to us, and we'll get you the information that you need. A PM 1433, unfortunately, that's not going to be compatible with this. The PM 1433 was discontinued a number of years ago. Does the system measure for gaze contingent and adaptive focus displays? Yeah, we've had some success with that. The lens has a focus capability. Most of these devices we would be measuring at infinity, but it can be focused to a closer region. We've also had some interest in creating some kind of like scanning system. And so it would be possible to move the device around the lens itself or move the camera around the device.
All right, everyone. I think we're going to wrap things up here. I appreciate everyone submitting these questions to Eric. If you didn't get your questions answered, please feel free to reach out to us at info@radiantvs.com. We will also have a report generated to send to our team to review your questions and answer them as if we didn't get to them today. Really appreciate you all coming and joining us for the webinar, and hope you have a great day. Thank you very much.